Everyone, let us continue with the second talk of the afternoon session. It's my pleasure to introduce our speaker, Tim Johnston. He is currently a PhD student at the University of Edinburgh. His research interest lies in numerical schemes, machine learning algorithms, and their convergence analysis. In this talk, he will be speaking about the performance of the Euler scheme for SDEs with discontinuous drift.
Thank you, Ying, and thank you to the organizers for putting on this conference. I know it's been a lot of work organizing a 4-week conference, but it's been really good. So today I'm going to talk about some recent results in numerics to do with the performance in numerical schemes when one has SDEs with coefficients which are quite irregular. So usually one expects that the more regular your coefficients are for the simulation of SDEs, the better the performance of numerical schemes. So if you have a small Lipschitz constant, for instance, you expect numerical schemes to perform well. And you expect the opposite. If you have a large Lipschitz constant, you expect numerical schemes to perform badly. However, the main takeaway of this presentation is that the accuracy of numerical schemes doesn't necessarily depend on the regularity of the coefficients. And in some cases, even with very irregular coefficients, one can obtain good convergence of numerical schemes for SDEs. So that's the main kind of takeaway. So I'm going to talk about strong convergence. I thought that this is probably familiar to a lot of you. I thought I'd just quickly talk about why we're interested in strong convergence rather than weak convergence. Generally, with applications, of stochastic analysis, one is interested in drawing from a certain measure, and in a sense, one's rarely interested in the actual true continuous time process. One's interested in finding some numerical approximation which is close to the object of interest in law. However, it's still useful to study strong convergence. In particular, I'll talk about convergence in LP, which is a form of pathways convergence, or maybe you could say technically it's not necessarily exactly pathways convergence, but it does mean for this to converge to 0, for these numerical approximations to converge to this continuous time object, one needs that mostly the simulations are close to the continuous time process for most realizations, most trajectories. So we're interested in strong convergence. One, it can tell you qualitative properties of the dynamics. For instance, the famous paper of Gyongyi and Krylov from 1996, strong solutions of SDEs is proven using the Euler scheme. So it can tell you something about the dynamics. Sometimes it can kind of tell you more. It also allows us to control the Wasserstein distance between the law of our approximations and the continuous time process in some metrics. By definition, if one has LP convergence, then one controls the Wasserstein distance here. And finally, for this multi-level Monte Carlo technique, which has become very popular in the last 20 years, one requires strong convergence. So for multi-level Monte Carlo, one splits. So say you're trying to work out the expectation of this quantity here, one splits it into a telegraphic sum, and then one can control each term in this sum. But one needs strong convergence of the numerical methods. So there's a few good reasons, in other words, to study strong convergence of numerical methods. So let's look at an SDE. We'll call the drift B, and we'll call the diffusion sigma. And let's look at the Euler scheme approximation. So this is the most simple numerical approximation. Essentially, one splits the time, index from 0 to infinity into intervals from 0 to 1 over n to 2 over n to 3 over n, so on. And one fixes the coefficients of the SDE at the start of each of these intervals. So that's the idea of the Euler scheme, which is, kind of the most natural numerical scheme in a lot of cases. So when is this Euler scheme approximation a good approximation of the continuous time dynamics? Well, kind of intuitively, one expects that if the dynamics aren't too sensitive to the space variable, then the convergence here will be good. So if when we change B or sigma a little bit, it doesn't change the value that much, one expects that the error induced by the discretization here won't be too severe. So the fact that B and sigma don't change too much when you change the state variable, that's exactly the regularity of B and sigma. So one expects with higher regularity, the numerical schemes will converge better. And in particular, one has the following classical results. So if we do have a Lipschitz assumption here on B and sigma, then in the general case, one obtains convergence, as we say, at rate 1/2. So here the error is equal to the step size to the power of 1/2, or at least it's bounded above by that. And if we have some additional smoothness in the drift coefficient, and we also have additive noise here, so the sigma is constant, then one can improve to convergence of rate 1. So the right-hand side here is equal to the step size times some constant. However, these two constants here depend on the Lipschitz constant L here. So when L is very large, these bounds blow up. So one expects that if B and sigma are very oscillatory, then these bounds here will be very large, and the numerical schemes will be quite inaccurate, even for large step size, or small step size rather. So given this, say if we pick an SDE with drift sine alpha x, as we increase alpha, as the drift here becomes more oscillatory, as it becomes more sensitive to the space variable, one expects that the performance of the Euler scheme will get very, very bad. So when the drift here is very sensitive to the position, one expects very bad performance with the Euler scheme using these kind of classical bounds. However, recent work has shown that this kind of heuristic explanation is actually not true at all. And the effect of the noise is to smooth the coefficients. So there's the following very strong result of Dariotis, Gerincher, and Ley. They have a few papers in this direction, but this is the most up-to-date result. So one has an SDE here with possibly multiplicative noise, but very importantly here, one has a so-called uniform ellipticity condition on the diffusion, which essentially means that one has enough noise, one has sufficient kind of regularization coming from the noise. And the regularity assumption on the drift here is extremely slight. All one asks of the drift is, for one, it's bounded, which is a strong restriction. But apart from that, just that it's measurable. So the drift here can be arbitrarily discontinuous, arbitrarily strange. But yet one recovers a result which is very close to the classical result for the Euler scheme. We almost recover the rate 1/2 here. It's a slight, we have a delta of error here, but we recover convergence of the Euler scheme at 1/2 minus. And furthermore, the constant here doesn't depend at all on the regularity of B. The constant here only depends on the supremum of B. So despite how bad B is, the performance of the Euler scheme doesn't degenerate. And the result is therefore entirely independent of the regularity of B. So one could take, for instance, just an example of a very discontinuous function. We take the sine of the sine function. This goes from 1 to -1, from 1 to -1 very quickly. But even as it becomes more and more oscillatory, the performance of the Euler scheme, somewhat surprisingly, doesn't blow up. So the key thing here is the noise has a regularizing effect. The noise smooths the regularity of the drift coefficient. So here we assume that both the drift coefficient and the diffusion coefficient were bounded. So if you know a bit about stochastic analysis, in this context, it's possible to apply Gerstner's theorem, both for the continuous time process and for the numerical schemes. And one can essentially think of them as a Wiener martingale with respect to a different measure. So that means lots of technical calculations one can apply to a Wiener martingale here and then transfer back to the continuous time solution and the Euler scheme using Gerstner's theorem. So let's look at how one bounds a crucial quantity. So this is a kind of model calculation. So we're looking at the expectation of a Wiener martingale evaluated at t and evaluated at the grid point prior. So t lies in the interval m/n to m+1/n. So, and here B is just measurable and bounded. So since B is just measurable and bounded, one expects for most omega, for most realizations, this quantity here will be large because one can't rule out that as the Wiener martingale moves forward, it goes across a jump. So for most omega, one expects this quantity to be large. But nonetheless, through the smoothing of the noise, in general, one can find a bound for this quantity. And so the technique here is very simple. One just writes out this expectation through the formula of the Wiener martingale. Since this is just a Gaussian random variable with variance S, one writes it the standard way, just by integrating over the density. And now we have this expression, and given it's an explicit expression, we have this explicit density. It's easy to differentiate. Given that this is integrable, one can bring the differentiation operator inside the integral. And it's a simple calculation to show this bound here, but the constant C here depends just on the supremum of B, because we merely bound B by its supremum here. And when we have this bound, since we have a bound on the derivative by the fundamental theorem of calculus, all we do is just integrate this from m of n to t, and we get a bound of this form. So if one fixes t and lets m over n be the grid point to the left of t, then one finds that this decays as n goes to infinity. Obviously, there's a lot more work to do before you prove convergence of the Euler scheme, especially strong convergence. And there's many tricks involved in this proof strategy. There's PD theory. There's this stochastic sewing lemma from a few years ago, which has a lot of utility. So there's a lot which goes into this result, but this is just a kind of a model calculation. So this is a very active area of research, the study of the Euler scheme for irregular coefficients. So the result presented prior, where we had rate 1/2 minus, this has been improved in a number of cases to a better rate, especially if one has a so-called Sobolev regularity, one can improve the rate here. If one has Holder regularity of the drift B, so if B is not discontinuous, but it's has some Holder regularity, one can also improve this convergence result here. There's another kind of alternative strategy utilized by Müller-Grönbach and Yardsasiva, where they consider coefficients which are piecewise regular. So in one dimension, this corresponds to having a finite set of points and having the function, the drift coefficient, be Lipschitz in between these finite sets of points, and discontinuous at the points potentially. And this strategy in particular allows for growth, because the main limitation of this result is that the coefficients are bounded. And furthermore, Müller-Grönbach and Yardsasiva have, along with their PhD student, Simelge, have proved a variety of optimality results. So they've proved that if you have discontinuous coefficients, you can never converge a rate faster than 3/4, no matter what numerical scheme you use. So both for the Euler scheme and any other numerical scheme, you can't converge faster than rate 3/4. So these are a bunch of positive results I just explained about when the Euler scheme converges very well. But there's also a sizable literature of negative results for the Euler scheme and indeed all numerical methods. So here, if we look at any numerical approximation here, so xn here doesn't correspond to the Euler scheme. It's just some approximation of the solution of the SDE xt using n evaluations of the noise. So there's a very good result of Müller-Grönbach from 2002, which shows that any numerical method for non-trivial SDEs can't converge quicker than at rate 1. So you can't do better than rate 1. And this is, the in general here is important because there are SDEs for which one can simulate exactly. For instance, geometric Brownian motion. If you know what WT is, one can deduce exactly what XT is for geometric Brownian motion. But as long as for generic SDEs where one doesn't have a certain condition satisfied, convergence is never better than at rate 1. And for general non-constant diffusion, it's never better than at rate 1/2. So there's a bunch of counterexamples as well, which have been constructed, which show that one can have very bad convergence in numerical methods. And each of these counterexamples has the property that the noise is somehow kind of strange. If one has uniformly elliptic noise, then convergence is usually pretty good. But if the noise is strange in some way, one can have very bad convergence. So for d greater than 2, one can find an SDE with bounded coefficients and bounded smooth coefficients as well, such that convergence is not at any polynomial rate. So for any delta greater than 0, the convergence is worse than at rate delta. These examples constructed are usually kind of artificial and strange, but actually an SDE which has a lot of application. So this Cox-Ingersoll-Ross process is used a lot in application, but this square root here by the noise makes simulating it very hard actually, and one can't converge at rate better than 2a over r squared. So for r large here, there's no way, no numerical method based on finite evaluations of the noise can converge particularly well. So it's not that the Euler scheme always converges well. There's also a bunch of cases in which it converges very badly. But given enough noise, convergence can often be recovered even for very bad situations. Okay, so now I'd quickly like to talk about the relevance of these numerics results for sampling algorithms, which I think is a kind of emerging topic. There's not much literature in this direction at the moment. So say one wishes to sample from a measure pi on RD. This is the classical case, familiar to most people probably here. One usually writes density in this form, e to the minus u. So one considers u the negative logarithm of the Lebesgue density. So theoretical bounds for sampling algorithms, of which there are many, that's become a very good literature, often have dependence on the Lipschitz constant of nablu. One kind of assumes that if nablu is very oscillatory, if it's irregular, then most sampling algorithms are predicted to perform badly by non-asymptotic bounds, that have been found. But what happens if nablu is irregular, which is actually quite relevant in a lot of cases? One can't expect necessarily that nablu is very smooth. One technique which has developed some attention is to use so-called proximal methods. So for proximal methods, one targets a new density, a smooth density. So we have a family of densities here, pi lambda. And this family of densities, pi lambda, have the property that when lambda is small, they're close to pi. So in particular, one obtains, I think, point-wise convergence of this density here to this density here. But they also have the property that when lambda is large, the nablu is regular. So it has a small Lipschitz constant for lambda large. So kind of balancing these two factors, one can recover convergence results. However, calculating the value of this regularized coefficient here is not so straightforward. It's related to this Moro-Uceda regularization a lot of time from convex analysis, and it's given as an infimum over the whole space. So one essentially has to solve a small optimization problem for every evaluation of this function and its gradient. So proximal methods recover theoretical convergence of the sampling algorithm. And I should say as well that proximal methods often actually perform better in practice, especially for using sampling algorithms for optimization. But one recovers theoretical convergence. However, the fact that one is now targeting a density which wasn't the original density that one was looking at does induce error, at least if you consider this a problem of sampling from the original density file, and it does induce computational cost. However, using the results that we discussed prior, so the numeric results, these, using the smoothing effect of the noise, essentially, we have a recent work where we're able to prove theoretical convergence of a sampling algorithm with irregular nablu, in particular discontinuous nablu, without using these proximal methods. So the technical challenge of this work was to apply the bounds for the Euler scheme, which are on a finite time interval, to an unbounded time interval. So the technical challenge was to prove uniform time bounds. So in particular, we considered a very popular sampling algorithm, the unadjusted Langevin algorithm, which is the discretization of the overdamped Langevin dynamics discussed in the prior talk. It's also known as the stochastic Langevin algorithm, has a lot of non-asymptotic bounds achieved. So we just discretize the overdamped Langevin algorithm with step size gamma greater than 0 in this case, and the Zn of just a sequence of IID resonance. And in many cases, again, with a huge family of literature, one has that the continuous dynamics in this case converge in a variety of metrics to the target measure pi, which is proportional to e to the minus u. There's a large family. So yeah, lots of convergence results have been proven for this algorithm. But as far as I'm aware, they all assume that the original density nablu is continuous. So our result is as follows. So we assume strong convexity, which is the nicest setting one obtained very easy. It's very easy to obtain convergence to equilibrium bounds. So from that perspective, everything's very simple. We assume that U is differentiable almost everywhere. So if U isn't differentiable almost everywhere, then this is generally not defined. If it is differentiable almost everywhere, given that the law of each xn plus 1 conditional on xn is absolutely continuous, the algorithm is well defined almost surely. And for this first bound, we assume just that NABLU obeys a growth bound. So actually using a very simple trick, one can obtain convergence with dimensional dependence 1/2 and the kind of step size error here 1/4. So this corresponds to the Euler scheme converging to the true solution rate 1/4. And this actually is quite a straightforward argument. There's nothing really to this one. But as well, if NABLU is discontinuous, and here we need that NABLU is discontinuous on C3 compact hypersurfaces. So it can't be discontinuous, for instance, on a hyperplane. We need it to be discontinuous on a compact set, and the boundary where it's discontinuous has to have some smoothness, has to be a C3 hypersurface. And outside of these points of discontinuity, it's a Lipschitz function. Then one achieves convergence at rate 1/2. So this gamma at 1/2 corresponds to the Euler scheme converging 1/2. And the dimensional dependence here is d to the 3/2. So the dimensional dependence is slightly worse, but the rate of convergence is slightly better. So this result therefore shows that one does not necessarily have to smooth bad gradients. In some cases, at least, one can just run the algorithm as usual. And even though the Lipschitz constant is in a sense infinite, one still recovers non-asymptotic theoretical bounds in Wasserstein distance. Okay, so just quickly to recap. So the performance of numerical methods doesn't necessarily depend on the regularity of the coefficients. A wide range of positive and negative results have been obtained for coefficients with numerical methods for SDEs with discontinuous coefficients. And we hope that these new methods can be applied to the performance of sampling and even for optimization algorithms. But there are a lot of open problems in this direction. For instance, when is convergence retained for bad gradients and when is smoothing necessary? Like I said, it seems like these proximal methods actually do give better practical results sometimes, at least for optimization problems. So perhaps sometimes the smoothing is actually necessary and one can't kind of cheat in this way. And as well, what about methods not based on the Euler scheme? So for instance, for accept or reject algorithms, things like that, I'm not aware. I mean, there's exactly a lot of cases, but yeah. So I think there's a lot of open problems to do with how much the smoothing effect of the noise can kind of overcome the irregularity of densities with low regularity. Yeah, and that's everything I wanted to say. Thank you.
Do we have questions?
So, not any results. Anyway,
I was wondering about the negative results. Do they also always assume constant step size, or you can also have a different step size schedule?
No, this is the thing. So there are so-called adaptive methods where one chooses the step size to do with. So if you're at if you're at point T1, you choose where to place T2, how big to pick the step size. But these are all, so you can have non-constant step size, but it has to be decided prior. So these bounds are all for where you pick some T1 to Tn, and then you run your simulation just knowing the noise at those points. And I think in general, the fact that you can't, the fact that the step size is non-constant here doesn't improve anything. But for adaptive methods where you choose at point, T1, where to pick T2, in some cases that can actually produce much better convergence. I think, for instance, for this Cox-Ingersoll-Ross process, if you have adaptive methods, the rate of convergence can be much better than as it is for non-adaptive methods. Yeah.
Thank you.
Thank you. Thanks for that talk. I have two questions. At the very beginning of your talk, you mentioned the fact that you are going to address the strong convergence, right? And not the weak one. Is there a technical problem or just didn't have any time to do that so far?
Well, so actually, I'm not so familiar with what the literature is like about the weak convergence. Actually, no, there's one paper from the early 2000s which deals with weak convergence. And I think rate 1 is recovered for weak convergence for bad coefficients. But in this kind of new research development in the last 10 years has focused mainly on strong convergence, and I'm not there might be more results than that one paper from 20 years ago about weak convergence, but yeah, off the top of my head, I'm not aware. But I think it would probably be, I mean, strong convergence obviously implies weak convergence, but in a lot of cases, you can probably do better than these results for weak convergence, yeah.
And at some point in your talk, you mentioned the stochastic queuing lemma. Do
Yeah.
you use rough paths?
What's that, sorry?
So I guess you don't use them. Rough paths.
Yeah, so I'm not sure. It might have some connection with rough paths, but
You don't lift to using both the incremental Brennan motions and integrated integrals.
it may be some connection with rough paths, but I think the stochastic Sohn lemma just tells you if you have this increment process, you can like form a process which is close to the increment process. I'm not completely sure how exactly they use the stochastic Sohn lemma, but it's definitely is used somehow in the proof strategy. I'm aware of the stochastic Sohn lemma, but in this case, I don't think it has a direct connection with rough paths. I think everything's considered in Ito sense, but maybe there are contentious to be explored with rough paths. That would be interesting.
Right. Do we have more questions? Probably I have one question. So in your theorem, you assume strong convexity and
Yeah.
this linear growth. So this can be relaxed or dropped because
So the strong convexity or the linear growth?
yeah, and both assumptions.
So I think linear growth could definitely be weaker to polynomial growth. And then with taming, I think that everything would probably be fine. The strong convexity, for the first result, I mean, this is actually just very, very simple calculation. It's just, so I think maybe you could relax the strong convexity, yeah. But because I mean, the convexity, this is the thing, the convergence to equilibrium bounds and numerics are quite kind of separate. So, you know, if you have convergence to equilibrium bounds, then probably you can, you know, you can do this in more general settings. And we're going to hopefully look into that in, you know, future work. But yeah, I think so.
Thank you, Tim. So if there are no other questions, let's thank Tim again.